Yesterday, October 16th, 2025. A new image of 3I Atlas emerged, instantly baffling scientists, deepening a profound mystery. From its core, a 6,000-kilometer plume erupted, not away from the sun, as physics dictates, but directly into its fiery heart. This defies all known laws, a cosmic impossibility, a signature of something profoundly unnatural. Such a bizarre feat, alien to our understanding, points to one truth: something built, not born. Can this truly be a comet? Tonight, we untangle the evidence, step by painstaking step. What we uncover will not merely rewrite comet physics, but unleash a revelation humanity is simply not ready for. If these mysteries resonate, if this profound anomaly pulls at your sense of wonder, then know your shared curiosity fuels this pursuit. We chase these enigmas, the ones others dare not touch, because you are here. Part 1. The Impossible Image. On October 16th, 2025, a single image jolted the astronomical community. It was a picture that, by all known laws of physics, simply should not exist. Data, painstakingly gathered on August 2nd and 3rd by the 2-meter twin telescope in the Canary Islands, had been processed and released through the astronomer's telegram. What it unveiled was so profoundly unsettling, so utterly defiant of expectation, that scientists worldwide paused, captivated by an impossible sight. Imagine it. A black circular mask at the center, meticulously placed to block the overwhelming brilliance of an object. Around this void, a familiar, luminous halo, the dusty coma, the cosmic breath of any typical comet. But then, from this cloud of gas and dust, something else emerged. A slender, ethereal jet, faint yet unmistakably real, reaching out approximately 6,000 kilometers into the void. And here lies the profound anomaly, the moment physics seemed to unravel. This jet pointed directly toward our sun. Perhaps you're thinking, comets have jets all the time. What's the big deal? Indeed, these dramatic plumes of material are a comet's signature. Born as frozen volatiles vaporize under the sun's warmth, spraying outward into space. Yet, there's a foundational principle taught in every introductory planetary science course. Comet jets, always without exception, point away from the sun. This isn't a mere preference or a common occurrence. It is an inescapable consequence of solar wind and radiation pressure. The sun exerts an outward force. Matter flows away. The physics is as simple, as undeniable, as water flowing downhill. But with 3I Atlas, this enigmatic interstellar visitor that has held our gaze for months, the water appears to be flowing uphill. Its jet defies this most basic cosmic rule. It's like witnessing a fountain where water arcs back into its nozzle, or smoke from a raging fire inexplicably sinking into the flames. This is the magnitude of the contradiction we face. The anti-solar direction, where jets and tails should naturally unfurl, remains eerily quiet, or at best, faintly illuminated. Instead, this defiant plume stretches sunward, an almost accusatory finger pointing directly at our star. Our understanding of the cosmos is built upon models, intricate frameworks, designed to explain observations, predict the unseen, and occasionally shatter when nature reveals an entirely new truth. This image doesn't merely challenge our comet model. It fundamentally fractures it. If this sunward jet is a genuine feature, not some elaborate illusion of data processing or a fleeting artifact, then our very textbooks on these ancient wanderers will need to be rewritten. The implications spread like fissures across a frozen lake. Could we be witnessing an entirely new class of cosmic object? Is some exotic, unknown physical process at play? One we've never encountered within our own solar system's comets? Or might this be evidence of something even more profound? Something that renders the familiar term comet utterly insufficient for what we are observing. These are not questions with easy answers. They are whispers of a deeper mystery, making this moment uniquely extraordinary. Yet, before we plunge further into its meaning, we must confront the towering uncertainty within the observatory itself. Astronomical images, particularly those coaxed from the faintest signals using advanced techniques, can be deceptive. They can conjure phantoms, artifacts, patterns that exist only in the algorithms, not in the physical universe. Laplacian filtering, the very method employed to enhance faint structures here, is potent, but not flawless. It can magnify noise, even fabricate features from the subtle trails of background stars during long exposures. Any seasoned astronomer understands this inherent vulnerability. The initial instinctive response to such a shocking image is always a healthy skepticism. We cannot simply accept this at face value. We must demand rigorous confirmation, multiple independent observations, diverse instruments, varied techniques, all converging on the same undeniable conclusion. But I can tell you, with a growing sense of unease and wonder, that confirmation has arrived. It has been quietly accumulating for weeks, a chorus of evidence. Earlier observations had already whispered of plumes at anomalous angles, at position angles near 280 degrees, that defied all conventional models. The venerable Hubble Space Telescope itself had captured fleeting glimpses of asymmetric features. Ground-based observatories, scattered across multiple nations, began to detect hints of this same impossible orientation. This isn't the isolated error of a single instrument. This is a convergence of multiple eyes on the cosmos, employing distinct technologies, yet all witnessing a shared, unsettling reality. While the scientific community hasn't yet reached absolute certainty, a luxury science rarely affords, the collective consensus is undeniably shifting from probably an artifact to likely genuine. The urgent whisper now is, we absolutely must explain this. When esteemed astronomers begin to publish peer-reviewed papers that treat the sunward jet as an undeniable feature demanding profound explanations, you know a critical threshold has been crossed. We have moved beyond skepticism, past dismissal, into a realm of shared fascination and profound scientific challenge. What unfolds next will not merely redefine our understanding of small celestial bodies. It may well pry open doors to entirely new cosmic paradigms we never even conceived. The clock is undeniably ticking. In a matter of days, 2 spacecraft will make their close approaches, their advanced instruments poised to capture data that could either decisively confirm or utterly demolish our current interpretations. It makes one wonder, how much more is out there, hidden in plain sight, waiting to dismantle our comfortable certainties? But before we arrive at that pivotal moment, we must grasp the true depth of this unfolding mystery. Because the sunward jet, as astonishing as it is, represents only the barest beginning. The very chemistry emanating from this object, the molecular story it tells, promises to make the jet itself seem almost prosaic by comparison. Part 2. The unmistakable sunward plume. A phenomenon emerged from the void, defying every expectation. A plume of material, streaming not away from the sun, but directly towards it. Before we surrender to the impossible, before we let ourselves believe in such a profound anomaly, the rigorous demands of science compel us to exhaust every mundane explanation. This is the scientific method's most profound gift, and its most frustrating, necessary burden. When confronted with something extraordinary, our first instinct isn't to celebrate, but to doubt. So, we must doubt with precision, with intelligence. The art and science of astronomical image processing is a forensic endeavor. We capture photons, ancient travelers from interstellar space, as they strike our detectors and transform into electronic whispers. Then, through intricate mathematical manipulation, we coax out structures too faint for the human eye to ever perceive directly. Every stage of this delicate process, however, is rife with potential for error. Background noise can mimic genuine features. Cosmic rays, silent assassins from space, can scar our detectors with bright streaks, easily mistaken for jets. Stars, tracing their slow arcs across long exposures, can leave trails that coincidentally align with intriguing directions. Even deconvolution algorithms, designed to sharpen blurred images, can introduce ringing artifacts, conjuring false structures from nothing. Yet, the brilliant minds scrutinizing 3I Atlas understood these pitfalls intimately. These researchers, seasoned by decades of peering into the cosmic abyss, did not simply apply a filter and declare victory. Their process was a relentless gauntlet of skepticism. They meticulously checked for contamination from background stars. They analyzed multiple epochs of observation, searching for evidence that the feature persisted, evolving in ways consistent with a genuine physical plume, not a fleeting processing ghost. They cross-referenced results from diverse telescopes, each with unique optical systems, distinct detectors, and varying atmospheric conditions. Crucially, they delved into the raw, unprocessed data, seeking the faintest whisper of a signal that could confirm a real entity before any enhancement algorithms had even touched it. What ultimately emerged from this exhaustive, almost brutal interrogation of the data was a reality increasingly impossible to dismiss. Indeed, the first faint whispers of this anomaly had surfaced in earlier observations, back in late July and early August. These initial glimpses hinted at peculiar plumes, extending at position angles that simply defied the logic of normal cometary behavior. For those unfamiliar, a position angle is our celestial compass, a way to map direction across the sky. 0 degrees points north, 90 degrees east, and so forth. Comet tails, by all known physics, should point in the anti-solar direction, a predictable angle determined by the comet's orbit and the sun's exact position relative to 3I Atlas. Yet, during these crucial early observations, that expected anti-solar direction was nowhere near where this baffling jet materialized. Suddenly, multiple independent research groups began cross-checking their own datasets. The Hubble Space Telescope, a sentinel with exquisite resolution, orbiting high above Earth's turbulent atmospheric veil, had captured images revealing an unmistakably asymmetric coma structure. Concurrently, ground-based observatories spanning continents, from Spain to Chile to Hawaii, independently documented these same unusual features. This unfolding narrative wasn't isolated. Astronomers, a global community of curious minds, constantly communicate. They share data, compare notes, challenge assumptions, when numerous independent teams, utilizing different instruments and methodologies, all begin to observe the same profound oddities. The convenient explanation of a mere processing artifact begins to fray, then shatter. Consider it a cosmic parallel to eyewitness testimony. If a single individual recounts something extraordinary, skepticism is a natural, healthy response. But if 10 distinct individuals, scattered across a vast city, each describe witnessing the identical strange event, from varying vantage points, using different recording devices at slightly staggered times, yet with striking consistency in their details. Then, our obligation shifts. We are compelled to take it seriously. This is precisely the crucible of evidence surrounding the sunward jet. Too many vigilant eyes, too many disparate instruments, too much undeniable consistency. These technical details, often overlooked, are the bedrock separating wild, fleeting speculation from the solid ground of observation. When scientists employ techniques like Laplace filtering, they are meticulously searching for subtle edges, for discontinuities in brightness, akin to turning up the contrast on a photograph to unveil the faintest, hidden details. This technique, however, is profoundly understood. We comprehend the artifacts it can generate. We possess the knowledge to distinguish between genuine cosmic features and mere filter-induced ghosts. The sunward jet, in every analysis, exhibits characteristics undeniably consistent with a real, three-dimensional structure erupting from the nucleus, not a flat, two-dimensional processing anomaly. Some researchers, driven by an insatiable curiosity, pushed even further. They meticulously analyzed the spectral signature of the material within different regions of the coma. If this jet was truly real, its spectrum should reveal the same molecular emissions as the rest of the coma, perhaps with altered ratios, depending on what was being preferentially ejected. And, with a chilling confirmation, the spectroscopic data unequivocally supported the presence of actual material in that impossible sunward direction, not merely empty sky or random noise. Molecular emission lines are not easily faked. Either those specific molecules are present, fluorescing under the sun's distant gaze, or they are utterly absent. There is no middle ground. So, where do we stand now? Amidst this cascade of evidence, the scientific community has transitioned, slowly, reluctantly, from initial disbelief to a cautious, almost reluctant acceptance. Research papers are now being drafted, not to explain away the sunward jet, but to assume its reality and grapple with its profound implications. This marks a monumental shift. We have crossed a critical threshold. From "is it real?" to "yes, it is real." So, what does it mean? And that second question, that deeper inquiry, proves far more intriguing and infinitely more unsettling. Because if this jet is indeed real, if material truly streams towards the sun, brazenly defying everything we thought we understood about cometary physics, then we are compelled to ask, what precisely is emerging from it? We must scrutinize its chemistry, its elemental composition, the very fingerprints of whatever substance is fueling this impossible backwards fountain. And when we do, when we aim our most sensitive spectrometers toward 3I Atlas and meticulously analyze the light it emits, we uncover something almost as bizarre as the jet itself. We detect nickel where our models predict iron, carbon dioxide where we expect water, and elemental ratios that simply make no sense for any known comet. The sunward jet may be the most visually striking anomaly, a beacon of the impossible, but it is the chemistry, the very essence of its being, that truly descends into the realm of the profoundly weird. Part 3. A nickel anomaly. Iron's absence. The existence of the jet, a phenomenon we are increasingly certain is real, immediately raises a profound and unsettling question. What precisely is erupting from this interstellar wanderer? The answer, when it arrived, was a paradox etched in light. Strong, undeniable emissions of neutral nickel atoms dominated the spectra, a clear signal shouting its presence. Yet, the expected companion, iron, was conspicuously, almost impossibly, absent. To decipher 3I Atlas's composition, astronomers employed a technique akin to cosmic forensics. When sunlight strikes molecules within a comet's coma, it excites them to higher energy states. As they return to their baseline, these molecules emit photons at specific, unique wavelengths, a spectral fingerprint as distinct as any barcode. By carefully dissecting this light into its constituent colors and measuring the intensity across various wavelengths, we can precisely identify the chemicals present and their relative abundances using humanity's most potent spectrographs, including the Very Large Telescope in Chile with its UV spectrograph. Researchers meticulously captured high-resolution spectra of 3I Atlas across multiple observation periods as it journeyed closer to the Sun. The discovery of metals in comets is not, in itself, surprising. Cometary dust grains naturally contain refractory elements like iron, magnesium, sodium, nickel, and calcium. Under intense solar radiation or sublimation, these metals can enter the gas phase, emitting their characteristic spectral lines. What truly startled the scientific community was not the presence of nickel, but its extraordinary ratio to iron in 3I Atlas. In typical solar system comets, iron is far more abundant than nickel, reflecting cosmic norms found in meteorites and across the universe. You expect to find more iron, always. Yet, during specific observation epochs, 3I Atlas displayed robust nickel emissions, while iron was almost entirely absent. Not merely diminished, but truly gone. Missing. This wasn't just unusual. It was, in the stark language of science, an extreme abundance ratio, academic code, for something fundamentally, deeply wrong. Some measurements indicated nickel to iron ratios orders of magnitude higher than anything ever recorded in another comet. It was as if an invisible hand had meticulously filtered out the iron, leaving only nickel behind. Such precise selectivity is simply not how natural processes usually unfold. A silence hangs over such data, a quiet unease that echoes the void of missing elements. But the chemical anomalies did not end there. They only deepened. The James Webb Space Telescope, a marvel of infrared astronomy revolutionizing our cosmic perspective, then focused its formidable instruments on 3I Atlas. JWST, uniquely attuned to infrared wavelengths, is perfect for detecting molecules like water, carbon monoxide, and carbon dioxide. What it revealed was another profound deviation. 3I Atlas's coma was overwhelmingly dominated not by water, as anticipated for a typical comet, but by carbon dioxide. The carbon dioxide to water mixing ratio registered an astonishing 8:1, 8 times more carbon dioxide than water. Consider that for a moment. Most solar system comets are essentially dirty snowballs, with water ice as the prevailing volatile. While they certainly contain other frozen gases, carbon monoxide, methane, ammonia, water almost always holds a comfortable lead. It's the primary substance that readily sublimates when comets become active at typical distances from the Sun. While comets with elevated carbon dioxide ratios do exist, they are exceedingly rare. Even within that unusual category, an 8:1 ratio stands out as truly extreme, a further fracture in our understanding. What could possibly explain such a bizarre chemical signature? Scientists quickly scrambled to propose natural mechanisms, seeking to reconcile these observations with known astrophysics. One intriguing hypothesis centers on metal carbonyl compounds, molecules where metal atoms are bonded to carbon monoxide groups. Nickel tetracarbonyl, NiCO4, is a known chemical that forms under specific conditions, with iron pentacarbonyl, FeNiCO5, as its analogous counterpart. Both are volatile, meaning they can sublimate at relatively low temperatures, far below those required for pure metals. If 3I Atlas somehow incorporated these compounds, their decomposition could release nickel and iron atoms, along with carbon monoxide. However, this explanation immediately faces significant challenges. The formation of such metal carbonyls demands very specific, cold, reducing environments, and their long-term stability is questionable. They are prone to decomposition when exposed to the ubiquitous ultraviolet radiation found throughout interstellar space. Could 3I Atlas have originated in some truly exotic stellar nursery, perhaps near a carbon-rich star, or within a molecular cloud with exceptionally unusual chemistry? While not impossible, such scenarios remain highly speculative. Crucially, even if metal carbonyls were present, this still doesn't fully resolve the perplexing nickel-to-iron ratio. Why would nickel carbonyls sublimate preferentially over their iron counterparts? Their sublimation temperatures, while distinct, are not dramatically different. This would necessitate an incredibly precise thermal environment within the nucleus, somehow driving out nickel while rigorously retaining iron. Some observations do suggest that iron emission became detectable only when 3I Atlas ventured within approximately 2.64 astronomical units from the Sun. This timing is consistent with a temperature-dependent release, yet it demands an exceptionally specific layering or composition gradient within the cometary nucleus, a geological arrangement that borders on the improbable for a natural formation. In the quiet hours, perhaps over late-night coffee in observatory break rooms, a more audacious, almost forbidden, possibility began to surface. What if a portion of this object is not entirely natural? What if these are not primordial materials, but substances processed or even engineered? Nickel alloys, after all, are pervasive in advanced technology. Stainless steel, superalloys for turbine engines, corrosion-resistant coatings, all rely on nickel. Nickel cyanide chemistry finds use in electroplating. If one were to construct a probe or spacecraft designed for the rigors of interstellar travel, nickel-rich alloys, prized for their strength and corrosion resistance, would be a logical choice. This is where profound caution becomes paramount. The chasm between unusual chemistry and alien artifact is vast and demands extraordinary evidence. We have compelling evidence of unusual chemistry. We do not, at this juncture, possess extraordinary evidence of anything more. Yet, the question persists, an uncomfortable, tantalizing whisper at the periphery of every scientific discussion. If this chemistry is truly natural, it forces us to fundamentally revise our understanding of comet formation, revealing gaps in our cosmic models. If, however, it is not natural, then the conversation shifts entirely, entering a realm of profound implications. The unsettling truth is that these compositional anomalies do not stand alone. They are threads in a broader tapestry of strangeness, a growing web that includes the persistent sunward jet, the unusual activity patterns, and other baffling oddities we are only just beginning to document. When anomalies start to accumulate, when enough pieces stubbornly refuse to fit into the established picture, a tipping point is reached. Dismissing each discrepancy individually becomes far more difficult than confronting them as a single, complex, and deeply enigmatic puzzle. And as we consider these patterns, there is one more aspect of 3I Atlas's behavior that defies any simple explanation. This object doesn't merely emit gas, it pulses. Part 4. The 4-hour enigma. The object, 3I Atlas, defies the expected, gentle outgassing of a typical comet. Instead, it expels material with startling, mechanical precision. Observers have detected rhythmic variations in its brightness and gas emissions, a pulse repeating roughly every 4 hours. Some data even suggests a shorter 2-hour period. possibly a harmonic echo. It's like witnessing a cosmic heartbeat, a deliberate rhythm hinting at an unknown underlying mechanism. In the natural universe, such precise periodicities often stem from rotation. The most immediate explanation for a comet displaying a 4-hour activity cycle would be a nucleus spinning with that exact period. Active regions on its surface would then cycle in and out of solar illumination, or our line of sight, as it turns. This isn't unheard of. Many cometary nuclei are irregular, elongated bodies tumbling through the void. If their jets are localized, perhaps where volatile ice deposits are exposed, or where the surface structure naturally funnels gas, then rotation would indeed create these on-off cycles. It's a perfectly sound, natural explanation. We know of comets with periodic outbursts. This rotational hypothesis fits within our current understanding. If this were the complete picture, the 4-hour pulse would be intriguing, a fascinating detail about 3I Atlas, but not fundamentally disruptive to our physics. It would simply refine our knowledge of this object's shape and activity. Yet, let's consider the precise requirements for such an explanation. For rotation to generate such a clean, unwavering 4-hour signal in both brightness and gas production, one would anticipate either an incredibly consistent active region or an exceptionally precise geometry. Small irregularities in the nucleus's shape, uneven solar heating, or shifts in subsurface ice as volatiles deplete, all should introduce noise, variation, and a gradual decay of regularity. Instead, the observations point to a remarkably stable periodicity. This isn't impossible, certainly, but it's noteworthy. It implies either an astonishing homogeneity in the nucleus's activity patterns, or that the mechanism driving these outbursts possesses some form of inherent self-regulation. A quiet unease settles in when nature appears too perfect. Perhaps we are simply unaccustomed to such cosmic precision. Another natural, yet more complex possibility involves a binary nucleus, two icy fragments locked in orbit around each other. If their orbital period aligned with 4 hours, tidal forces and mutual heating could conceivably drive periodic fluctuations in activity. Binary comets and asteroids are known phenomena. We have observed them, and their physics is well understood. If 3I Atlas were a contact binary, or even a separated pair, it could account for the periodicity without resorting to exotic hypotheses. But once more, this demands a fairly specific configuration. Crucially, we lack direct imaging of the nucleus to confirm or dismiss this. The object remains too distant, too faint, for even our most powerful telescopes to resolve its core directly. A frustrating veil persists. Then there's the ever-present shadow of observational bias. Periodicities can sometimes be artifacts of our own methods, an echo of how we collect data. If telescopes observe at regular intervals, perhaps due to scheduling demands or Earth's rotation, they might inadvertently impose a false rhythm onto inherently noisy data. Astronomers are acutely aware of this and employ sophisticated statistical techniques to mitigate it. But the concern always lingers. Could this 4-hour period be a real signal within our data, yet not a true reflection of the comet itself? Possible. However, the fact that multiple independent observing campaigns have consistently reported this timing strongly argues against it being a mere artifact. Still, scientific caution dictates vigilance. The universe rarely gives up its secrets easily. Now, we step into a more speculative realm, exploring interpretations that venture beyond the established boundaries of cometary physics. If the 4-hour pulse is unequivocally real, and not simply explained by rotation or binary dynamics, what other forces could possibly be at play? Could an internal mechanism exist? A hidden reservoir of volatiles periodically released through some controlled vent in a typical comet? internal pressure accumulates as ice sublimates beneath the surface, eventually breaching through structural weaknesses, causing unpredictable outbursts. But these events are almost universally chaotic, irregular, driven by random fractures and collapses, utterly devoid of a neat, predictable schedule. A sustained, regular 4-hour cycle, however, suggests either an extraordinary, almost impossible coincidence of natural factors, or something far more deliberately organized. Consider a scenario where the nucleus possesses an internal structure, chambers or pockets where gas accumulates, releasing only when pressure reaches a specific threshold. If these chambers were uniform in size and the sublimation rate remained constant, one might observe periodic releases. It's akin to a terrestrial geyser, where groundwater heating follows a predictable cycle based on reservoir volume and heat input. But comets are not geysers. They lack stable underground cavities, and certainly don't possess regulated heat sources. They are, by definition, porous, crumbly rubble piles of ice and rock, not sophisticated plumbed systems with valves and chambers. Unless, and here, we consciously step into the realm of the truly speculative, unless this object harbors an engineered component. If its structure incorporates materials or design elements explicitly intended to regulate gas release, then a periodic cycle, driven by intentional mechanisms, becomes imaginable. Vents that open and close, reservoirs that fill and empty, systems meticulously designed to maintain internal pressure or ration precious volatiles for an extended journey across the cosmos. This narrative feels like science fiction because, for now, it is science fiction. A wild leap of imagination awaiting empirical evidence. Yet, this persistent 4-hour pulse, when considered alongside the sunward jet and the nickel-dominated chemistry, adds another unsettling anomaly to an already growing pile. One more intriguing, albeit complex, angle remains to explore. What if metal carbonyl compounds are deeply involved in this outgassing, and their formation or breakdown follows a cyclic chemical process that inherently introduces periodicity? Envision a feedback loop. Solar heating drives sublimation, which in turn cools the surface. This cooling then allows carbonyls to recondense, restarting the cycle. Such a process is thermodynamically plausible, given precise conditions. However, it would demand incredibly specific chemistry and remarkably stable conditions across the nucleus. It's not the immediate explanation one would instinctively grasp, but it's not impossible. The 4-hour pulse matters because it represents yet another data point that refuses to comfortably align with our standard cometary models. Considered in isolation, it might be intriguing, but ultimately explainable. Yet, when viewed alongside the sunward jet and the nickel-dominated chemistry, it profoundly amplifies the unsettling sense that 3I Atlas operates by a different set of rules entirely. The core question now becomes whether these rules are unique to this singular object, or if they hint at a broader, unknown category of interstellar visitors we are only just beginning to comprehend. Because here lies the stark, urgent reality. We will not have the luxury of studying this object leisurely for decades. We possess one fleeting chance, a narrow window to capture close-up data from spacecraft, fortuitously positioned at the right place and time. That window is not merely opening, it is now. In days, instruments aboard 2 distinct missions will sweep through the nearby void, their sensitive sensors locked onto this profound enigma. What they ultimately discover, or fail to discover, will irrevocably shape our understanding for generations. The stakes are immense. Part 5. The cosmic clock is relentlessly ticking. This fleeting window may be our singular chance to truly glimpse the enigmatic 3I Atlas up close. In the profound silence of space, Close encounters between human-crafted probes and celestial wanderers are exceptionally rare. They are precious opportunities, typically born from decades of meticulous planning or seized by an almost unbelievable stroke of luck. 3I Atlas, however, arrived in our solar system unannounced, tracing an orbit we had no way of predicting. It only became visible to us after it had already rounded the sun, hurtling outward, back toward the deep interstellar void. Sending a dedicated mission to rendezvous with it is simply impossible. There isn't enough time to conceive, design, build, and launch a probe capable of catching an object already accelerating away into the darkness. Yet, in a twist of cosmic fortune, 2 spacecraft, originally dispatched for entirely different objectives, will pass within detectable range. This critical period coincides precisely with when the comet remains observable. The European Space Agency's Hera mission, designed to meticulously study the aftermath of NASA's DART impact on the asteroid Dimorphos, has an unexpected flyby window. This opportunity spans from October 25th to November 1st, 2025. During these crucial days, Hera will come within approximately 8 million kilometers of 3I Atlas. By the exacting standards of spacecraft missions, this isn't a close encounter, not a true flyby where we skim past at intimate range. Yet, it is close enough for certain sophisticated instruments to gather invaluable data. Hera is equipped with cameras, spectrometers, and particle detectors, all meticulously designed to analyze asteroid surfaces and their dust environments. These very instruments can be partially retargeted. They can pivot, at least in part, to observe the comet's swirling coma and its extended tail structure. NASA's Europa Clipper, currently en route to Jupiter's ice-covered moon, finds itself with a similar serendipitous opportunity. Its window opens between October 30th and November 6th. Again, we speak of millions of kilometers, not mere hundreds or thousands. Europa Clipper will not resolve the nucleus itself. It won't capture close-up images, revealing surface intricacies. But its spectrometers possess the capability to analyze the light filtering through the coma. Its plasma instruments can detect the charged particles, those fragments stripped from the comet by the relentless solar wind. Even its magnetometers might register the subtle signatures of magnetic draping, where the interplanetary magnetic field gently bends around the comet's ionized gas cloud. The true value of these unplanned flybys lies in the sheer diversity of measurements they promise. Optical imaging from Earth provides a grand, large-scale view, the majestic jets, the expansive coma, but it struggles to differentiate between distinct chemical species or precisely measure the physical properties of individual dust grains. Ground-based spectroscopy offers compositional insights, yet it battles limitations imposed by Earth's thick atmosphere and the comet's inherent brightness. Spacecraft instruments, even from significant distances, can pierce through these veils. They can access wavelengths utterly blocked by our atmosphere, directly measure particles, and observe without the blurring and scattering that relentlessly plague ground-based observations. Imagine the implications if either Hera or Europa Clipper were to detect strong nickel emission. That would independently corroborate the strange spectroscopic oddity we've already witnessed from Earth. If they meticulously map the coma's structure and uncover asymmetries consistent with that perplexing sunward jet, it would dramatically strengthen the argument for a genuine physical feature, not merely a processing artifact. And what if plasma detectors pick up unusual ion compositions or unexpected populations of particles? Such findings could hint at exotic chemistry, perhaps even non-natural materials, outgassing from the nucleus of 3I Atlas. Conversely, if the spacecraft observe nothing out of the ordinary, if their data paints a picture of a comet that is chemically and physically unremarkable, then we would be forced to re-evaluate. We would have to reconsider whether the ground-based anomalies were misinterpretations or perhaps even measurement errors. There is one predicted opportunity that particularly captivates plasma physicists: the comet's ion tail. That luminous stream of charged particles torn away by the solar wind is projected to intersect with one or both spacecraft. When this happens, instruments designed to measure the local space environment will suddenly find themselves immersed. They will be bathed in plasma directly derived from the comet itself. They will detect ions of whatever molecules are being ionized within the coma. Water ions, carbon monoxide ions, carbon dioxide ions, and yes, if present in sufficient quantities, metal ions like nickel and iron. The mass spectrometers aboard these missions can distinguish between different ions based on their mass-to-charge ratios. This offers us a direct, undeniable measurement of the tail's true composition. Moving beyond mere inference from spectroscopy, magnetic field measurements present yet another diagnostic tool. As the solar wind collides with a comet, the interplanetary magnetic field becomes draped around the obstacle, forging a characteristic pattern. The precise shape and strength of this draping are dictated by the comet's outgassing rate, the intricate composition of its coma, and the efficiency with which ions are created and interact with the ambient field. Any deviation from the expected pattern could signal unusual plasma physics or unexpected conductivity. These in turn might point to exotic chemistry or even entirely unforeseen material properties within 3I Atlas. But let us be realistic about the inherent limitations. These spacecraft are not on dedicated comet flyby missions. They operate under stringent schedules, with primary objectives that do not revolve around 3I Atlas. Hera must reach Dimorphos and execute its comprehensive survey. Europa Clipper must meticulously conserve power and momentum for its critical arrival at Jupiter. Redirecting instruments toward the comet demands precious fuel for attitude adjustments. It competes directly with other planned observations and risks disrupting scheduled activities. The vast distances involved mean that resolution will inevitably be limited. We will not receive intricate surface maps or breathtaking close-ups of active vents. Instead, we anticipate contextual data, tantalizing compositional hints, and crucial environmental measurements. There is also the formidable challenge of timing. The flybys unfold over spans of days, and the comet itself is a dynamic entity moving, changing, potentially varying its activity due to that inexplicable 4-hour pulse or other unknown factors. Coordinating observations, ensuring instruments are perfectly aimed, and capturing data at optimal moments demands meticulous planning and a considerable measure of luck. Mission planners are striving their utmost, navigating a landscape of constraints and uncertainties. Historically, opportunities of this nature have been a mixed bag. When Oumuamua, the first confirmed interstellar object, tumbled through our solar system in 2017, no spacecraft was positioned to observe it intimately. Everything we learned came from telescopes on Earth and in Earth orbit, and it proved insufficient to definitively resolve the intense debates surrounding its true nature. By the time we truly grasped its strangeness, it had already passed perihelion and was fading irrevocably from view. We never received a second chance. Comet Borisov, our second confirmed interstellar visitor, arrived in 2019, granting us more time for study. But again, no spacecraft encounters, only remote observations were possible. 3I Atlas represents our third confirmed interstellar object, and for the very first time, we have spacecraft close enough to potentially augment our remote observations with invaluable in situ measurements. This is not the comprehensive mission we would design if we had years to prepare, but it is, unequivocally, infinitely better than nothing. What Hera and Europa Clipper detect, or fail to detect, will resonate through scientific papers for years to come. Their findings will shape models, either settling or intensifying debates, and ultimately guide how we interpret all future interstellar visitors. The next few days will reveal whether these anomalies are robust, reproducible across different measurement techniques. If the spacecraft data aligns with the ground-based oddities, confidence in the reality of those oddities will skyrocket. If, however, the spacecraft data contradicts or simply fails to observe what telescopes have reported, then we will face a significant calibration problem or a modeling issue that demands resolution. Either outcome, it must be said, is scientifically invaluable. Either outcome brings us closer to truly understanding what 3I Atlas actually is. Yet, as we await those pivotal flyby results, we must remember there is more to this story than just this single object. The anomalies don't merely cease with the sunward jet, or the nickel chemistry, or that rhythmic pulse. When one begins to meticulously catalogue every peculiar aspect of 3I Atlas, when you line up all the observations that simply refuse to fit a profound realization dawns. This object is an embarrassment of riches for any seeker of anomalies. It isn't merely one or two oddities. It is 15, perhaps even more. Each one demands an explanation, each adding immense weight to the unsettling sense that we are missing something truly fundamental. Part 6. The Dossier of Anomalies. We are now at Part 6, a critical juncture. It is time to open the forensic file, to meticulously assemble the dossier of 3I Atlas. We are not just counting peculiarities. We are cataloging every piece of evidence that sets this object apart from any comet we thought we knew. Individually, some of these might be dismissed as quirks, as observational blips, or the fuzziness of measurement. But when laid out, one after another, they begin to sketch a portrait of an object that simply refuses to obey the known laws of the cosmos, defying our deepest models. Anomaly 1. The missing tail. Comets are defined by their grand, luminous tails, sweeping across millions of kilometers of space. Dust plumes arc gracefully. Ion streams stretch taut, driven by the solar wind. But 3I Atlas, despite its activity and brightness, displays only muted, dramatically shorter tail structures. It possesses a coma, yes, but the expected grand spectacle is absent. It is almost as if the ejected material is not being properly swept away, or its production rate is strangely subdued compared to its visible glow. Anomaly 2. The impossible sunward jet. We have spoken of this before, but it bears repeating. Material actively streaming towards the sun, directly opposing the immense forces of radiation pressure and solar wind. This is not just unusual. It is a fundamental violation of every principle we understand about cometary physics. This single observation, by itself, should have sounded alarms. Anomaly 3. The skewed metal signature. A high nickel to low iron ratio. This extreme imbalance in elemental abundances does not align with the cosmic norms of our solar system, nor even with typical interstellar clouds. It hints at a genesis in some truly exotic environment, or perhaps a chemistry we can barely conceive. Anomaly 4. A coma dominated by carbon dioxide. Most comets are rich in water ice. 3I Atlas, however, dramatically reverses this expectation, with CO2 outweighing water by a factor of 8. This suggests a birth in a profoundly cold, carbon-rich cradle, perhaps orbiting a different kind of star, or forged within a molecular cloud utterly distinct from our own solar system's origins. Anomaly 5. the suppressed water. This is not merely a rephrasing of the CO2 dominance. It underscores a profound absence. Water, the most ubiquitous cometary ice, appears strangely depleted or somehow sequestered within 3I Atlas. This specific lack carries deep implications for its formation story and its entire thermal journey through space. Anomaly 6. Rhythmic, periodic outbursts. The precise 4-hour and even potential 2-hour cycles of activity we observed. Such regular, almost mechanical, patterns strongly suggest an organized internal structure or very specific geometric dynamics linked to its rotation. It is not random. It is almost timed. Anomaly 7. The asymmetric coma. While some cometary coma exhibit minor asymmetry, 3I Atlas presents pronounced, unsettling irregularities. Its shape defies our standard models for dust and gas distribution. The sunward jet certainly plays a role, but even beyond that, the overall structure of its glowing envelope remains profoundly strange. Anomaly 8. Non-random orientation shifts. Reports emerged of plumes and jets altering their direction in ways that seemed disconnected from orbital mechanics or predictable rotational effects. This is a more elusive anomaly, difficult to definitively quantify, yet it deepens the unease. It suggests the object's activity is not merely a passive response to its environment. Anomaly 9. An extreme negative polarization signature. Polarimetry. The study of how light is polarized usually reveals specific characteristics for cometary dust, but 3I Atlas displayed a deep negative polarization branch. At certain scattering angles, the light was polarized in the opposite direction to what we typically observe. This points to highly unusual dust grain properties, a different size, composition, or even shape than any comets we have encountered from our own solar system. Anomaly 10. The ghostly anti-tail, captured by Hubble. Even before the more dramatic imagery, early Hubble observations hinted at a narrow, sunward-pointing structure, an anti-tail. At the time, it was easy to dismiss as observational noise or a faint dust feature. Yet, looking back, it now appears as an unmistakable precursor, an early warning of Anomaly 2, the defiant sunward jet. Anomaly 11. Premature outgassing of water and hydroxyl. Water and hydroxyl emissions were detected when 3I Atlas was still several astronomical units from the Sun. This is far beyond the distance where significant water ice sublimation typically begins. This early, almost aggressive activity suggests either an unusually exposed, volatile-rich surface, or perhaps a hidden heat source driving sublimation beyond mere solar irradiation. Anomaly 12. The perplexing green color shift during a lunar eclipse. Comets can indeed glow green from carbon-bearing molecules like C2, yet 3I Atlas displayed this green hue even when spectroscopy showed low C2 abundance. The shift occurred precisely during a lunar eclipse, as Earth's shadow altered the comet's illumination. This implies a change in its scattering or emission properties that defies simple explanation, adding another layer of visual mystery. Anomaly 13. The presence of hydrogen cyanide. HCN was definitively detected at a heliocentric distance of 2.13 astronomical units. While its ratio to CN was similar to solar system comets, a rare moment of familiarity, the very presence of cyanide compounds deepens the chemical enigma. It becomes even more unsettling when we recall how nickel cyanide chemistry finds its purpose in industrial processes right here on Earth. Anomaly 14. The abrupt shift in the nickel-to-iron ratio. Iron emission only became detectable once 3I Atlas crossed within approximately 2.64 astronomical units from the Sun. Before this precise threshold, nickel dominated, almost entirely devoid of iron. Afterwards, iron suddenly appeared. This temperature-dependent release pattern hints at a layered composition or distinct volatile reservoirs, each sublimating at different thresholds. But the sheer sharpness of this transition is profoundly unusual, almost like a switch being flipped. Anomaly 15. The delayed or even withheld imagery from Mars orbiters. 3I Atlas made a relatively close pass to Mars, within 29 million kilometers, around October 3rd. Spacecraft like the ExoMars Trace gas orbiter and Mars Express possess powerful imaging capabilities that surely captured this event. Yet, the public release of such high-resolution imagery has been conspicuously slow, or in some cases, while bureaucratic processes, data processing, or mission priorities could explain such delays, it undeniably deepens the atmosphere of mystery. One cannot help but wonder if something within those images is undergoing a very careful, perhaps even urgent, review before it ever sees the light of day. Each of these anomalies, taken in isolation, might be neatly explained away. A peculiar dust composition, an exotic birthplace, a fleeting observational artifact, or simply bureaucratic delays. But when you confront a dossier of 15 such anomalies, when pattern after pattern refuses to conform, a profound question emerges. Is our standard cometry model simply insufficient for visitors from beyond our solar system? Perhaps objects forged around alien stars, steeped in different radiation fields, composed of entirely different primordial chemistries, simply operate by different rules. Perhaps the cosmic laws we have painstakingly derived from our own solar system's comets simply do not apply to these galactic travelers. Yet, there is a persistent, unsettling whisper, a thought that dares to surface, however quietly. What if, just perhaps, we are observing something that is not entirely natural? This is the speculation that lingers in the shadows, the one no one wants to voice too loudly, fearing it sounds like fringe science or sensationalist fodder. But the whisper endures. It grows louder with every new piece of data that refuses to fit. Nickel without iron, cyanide compounds, rhythmic pulses, jets defying the sun. No single anomaly screams artificial, but together they form a constellation of profound oddities, forcing us to question everything we thought we knew. So, let us, for a moment, entertain this radical speculation directly, not as a definitive conclusion, but as a crucial thought experiment. What if some fundamental component of 3I Atlas, be it a surface coating, an internal structure, or even a deliberate payload, involves engineered materials? What observable signatures would such a possibility leave? And do those predictions align with what we are currently witnessing? Part 7. The Engineered Alloy Hypothesis, a Disturbing Blueprint. The perplexing chemistry and rhythmic emissions from 3I Atlas have forced us to confront possibilities once confined to fiction. Among the most audacious hypotheses, debated in hushed tones, lies an unsettling idea. What if parts of this interstellar visitor are not merely natural formations, but engineered structures? Not the entire object, perhaps, but a shell, a hidden layer, or a core component embedded within what otherwise appears to be a typical comet nucleus. It's an idea that feels ripped from a cinematic screenplay. Yet, the unsettling logic demands our attention. Our own terrestrial technology relies heavily on nickel alloys. From the everyday resilience of stainless steel in kitchen sinks to the critical components of spacecraft, these metals, often containing chromium and nickel, offer unparalleled resistance to corrosion. Consider the extreme demands placed upon superalloys in jet engines or rocket nozzles. These materials, predominantly nickel-based, must endure searing temperatures and corrosive environments with resilience. Trade names like Inconel and Hastelloy represent the pinnacle of strength and durability. If an advanced civilization sought to construct a probe or instrument package designed to traverse the vast, unforgiving emptiness of interstellar space for millions of years, withstanding relentless cosmic rays, microscopic impacts, and the subtle erosion of trace gases, then nickel alloys would be more than a choice. They would be a logical imperative. They are built for survival. Beyond structural integrity, nickel cyanide chemistry plays a role in electroplating, a process where a protective, thin layer of nickel is precisely deposited onto another metal. This technique, crucial for enhancing durability or for aesthetic finish, relies on cyanide ions to bind the nickel, meticulously controlling the deposition. Should one be coating a structure with nickel for extreme longevity, these nickel cyanide baths would be essential. Yet, even the most robust defenses eventually succumb over eons. Subjected to the brutal conditions of deep space, unfiltered ultraviolet radiation, ceaseless thermal cycling, the relentless abrasion of micrometeorites, such advanced coatings would inevitably begin to degrade. A nickel-rich surface layer would slowly ablate, flaking away atom by atom. As this protective shell fractures, it would steadily release individual nickel atoms and, crucially, residual cyanide compounds into the cosmic void, a silent shedding of its very essence. Now, envision this. A nickel-coated structure, precisely as we've described, lies hidden. Perhaps it's embedded deep within the icy heart of a comet nucleus, or securely attached to its surface. As 3I Atlas draws closer to the Sun, the familiar heat begins its work. The surrounding ice warms, then vaporizes, releasing its ancient stores of gas and dust. But if our hypothetical structure is even partially exposed, it too will begin to heat. Any lingering volatile compounds, any remnants of its degraded surface, would start to outgas. What would we detect? Emissions of nickel, certainly. Potentially, telltale signatures of cyanide species. And, depending on the intricate chemistry involved, a spectrum of carbon-bearing molecules. Crucially, the ratios of these elements would tell a different story. They wouldn't align with the expected profile of typical cometary material. We wouldn't merely be observing sublimated ice. We would be witnessing the profound breakdown products of engineered materials, inextricably mingled with the comet's natural exhalations, a chemical signature unlike any we've ever encountered. This chilling scenario offers a potential, albeit radical, explanation for the peculiar observations of 3I Atlas. The unusually high nickel-to-iron ratio, it could be accounted for if the engineered component utilized a nickel-rich alloy, deliberately crafted with minimal iron. The perplexing detections of hydrogen cyanide? They would make sense if cyanide chemistry was integral to the material's production or surface treatment. And the puzzling dominance of carbon dioxide? This might point to the structure containing carbon-based components, perhaps polymers or specialized organic coatings that degrade into CO2 under the relentless assault of ultraviolet radiation and solar heating. Even the rhythmic, almost mechanical, 4-hour pulse of activity from 3I Atlas begins to take on a new, unsettling meaning within this framework. If the engineered component possesses vents, valves, or other structural features designed to regulate gas flow, either by deliberate design or as a consequence of its slow, inexorable degradation, then periodic releases become not just possible, but expected. Picture a sealed compartment, slowly filling with sublimated gas from the surrounding ice, pressure steadily building. Then, a release. A vent opens. A crack gives way. The gas escapes, pressure drops, and the cycle begins anew. A 4-hour period would simply be the characteristic timescale for this particular system, dictated by the compartment's size, the sublimation rate, and the resistance of its outflow vent. A heartbeat, perhaps, of something artificial. And what of the enigmatic sunward jet? It loses much of its mystery if we consider it driven by something far more deliberate than random sublimation. Imagine the engineered structure features a directional vent, a finely crafted nozzle or opening, oriented by chance or design to point sunward as the object tumbles through space. Gas expelled from such a vent would generate a powerful jet precisely in that direction, irrespective of the sun's position relative to the comet's bulk. It wouldn't be merely battling radiation pressure. It would bypass the chaotic mechanisms of natural outgassing, releasing material from a specific point with enough focused force to locally overpower the solar wind. A directed expulsion, a controlled breath. The entire narrative, when laid out, begins to sound disturbingly plausible. It's a path that, once taken, is hard to abandon entirely. But we must temper this fascination with brutal honesty. This hypothesis, this blueprint of something alien, demands an extraordinary chain of coincidences. It requires, first, that an advanced civilization built such a probe or object. Second, that this creation somehow found its way into the vastness of interstellar space. Third, that it then serendipitously traversed our solar system. And finally, that it degraded just enough to release its telltale signatures, yet not overtly reveal its artificial nature. Is that not an almost impossible series of happenstance? Furthermore, it mandates that we are either misinterpreting the data or perhaps overlooking a subtle, natural explanation that could equally account for these same baffling observations. The scientific community has a stark term for such profound speculation. Carl Sagan's principle that extraordinary claims demand extraordinary evidence. The premise is elegantly simple. The more unusual, the more paradigm-shifting a claim, the higher the burden of proof. To suggest 3 I-Atlas exhibits unusual chemistry is a modest claim, requiring only modest evidence. But to assert it is partially artificial, that crosses into the realm of the extraordinary, demanding evidence of an equally extraordinary caliber. Do we possess that level of undeniable proof? No, we do not. What we have are compelling anomalies, suggestive patterns, and a persistent absence of fully satisfying natural explanations. This, critically, is not the same as definitive proof of artificiality. We must always remember the universe's boundless creativity. Natural mechanisms possess an astonishing capacity to surprise us. Under exotic conditions, chemistry can yield results far beyond our current understanding. Interstellar environments, by their very nature, remain largely unsampled, their mysteries barely touched. While we have meticulously studied comets within our own solar system, they all share a common origin, formed within the same protoplanetary disk, from similar starting materials under comparable conditions. But an interstellar comet, born around a different star, perhaps within a molecular cloud of vastly different metallicity, irradiated by a unique spectrum of starlight, could simply be weird, profoundly alien, without being artificial. Such an object might not be a sign of engineering, but a profound lesson. It could reveal that the normal chemistry of comets is far more diverse, more astonishing than we ever dared to imagine. Yet, to dismiss such speculation entirely would be to betray the very spirit of scientific inquiry. Science progresses precisely by daring to consider the impossible, by rigorously testing every possibility, and then by either confirming or decisively ruling them out. The engineered alloy hypothesis, despite its radical nature, is testable, at least in principle. Imagine the evidence that would shift the paradigm. If future spacecraft flybys were to detect particles or ions with isotopic ratios utterly inconsistent with any known natural nucleosynthesis, that would be a smoking gun. If high-resolution imaging were to reveal unambiguous geometric structures, impossibly straight edges, or regular patterns utterly alien to the chaotic formation of natural rubble piles, that would be profoundly compelling. And if advanced spectroscopy were to identify molecules that only exist as byproducts of industrial processes, with no plausible natural formation pathway, then we would confront this idea with the utmost seriousness. The universe would be speaking to us in a language of design. Conversely, if future observations uncover elegant, natural mechanisms that fully explain the nickel dominance, the carbon dioxide excess, and the sunward jet, without ever needing to invoke engineered materials, then the hypothesis would gracefully collapse under the weight of Occam's razor. The simpler explanation, the one requiring fewer assumptions, would prevail, and the mystery would simply transform. But for now, we remain in an uncomfortable in-between zone. The data is undeniably strange enough to ignite our deepest curiosities, to make us question everything. Yet, it remains tantalizingly short of definitive proof, insufficient for any final conclusion. This very moment, however, is uniquely fascinating precisely because our speculation isn't happening in a void. We stand on the precipice of obtaining new, critical data. The forthcoming flyby results will either bolster the case for these exotic, engineered explanations, or they will just as decisively weaken it. The truth is coming, but even as we eagerly await those revelations, another layer of this story unfolds, adding an unexpected depth to the enigma. Sometimes, what remains unseen, what is withheld, speaks as loudly as what is plainly revealed. In the curious case of 3I Atlas, there are missing pieces, whispers of unexplained delays, and images that have yet to surface. These absences, these silences, weave an uncomfortable thread of intrigue through the very fabric of the mystery. What secrets are still hidden? Part 8. The Martian Silence. In a cosmic age awash with instant data, where every celestial whisper is amplified and shared, a profound silence can often speak the loudest. It is the absence of information, the void where observations should be, that now haunts our understanding of 3I Atlas. This is not just a missing tweet or a delayed paper. It is a conspicuous gap in the cosmic record, a signal in its own right. In early October, 3I Atlas swept past Mars, positioning itself perfectly for an unprecedented close-up. Our Martian sentinels, a fleet of advanced orbiters, should have captured its enigmatic form with unparalleled clarity. Yet, the imagery from these missions has been conspicuously slow to emerge, in some instances entirely absent from public view. A strange quiet has fallen over the data streams. Consider the instruments poised above the red planet. The European Space Agency's ExoMars Trace gas orbiter, designed for atmospheric study, carries cameras perfectly capable of capturing celestial bodies. Its venerable counterpart, Mars Express, has orbited Mars since 2003, also equipped with impressive imaging capabilities. Then there is NASA's Mars Reconnaissance Orbiter, home to the High-Resolution Imaging Science Experiment, or HiRISE. This camera is so acutely powerful, it can discern objects less than a meter across on the Martian surface itself. While aimed at a comet millions of kilometers distant, HiRISE wouldn't achieve that same surface-level detail. It could undoubtedly resolve the delicate coma structure, the precise geometry of its jets, and its overall morphology, with a clarity far surpassing any Earth-bound telescope. 3I Atlas made its closest approach to Mars around October 3rd, at a distance of approximately 29 million kilometers. This was not a direct flyby, certainly, but it rested well within the optimal imaging range for these sophisticated spacecraft instruments. The cosmic alignment was perfect, the opportunity undeniable. One cannot help but wonder, were those instruments truly directed at 3I Atlas? And if they were, what could possibly explain the prolonged silence surrounding their findings? Of course, there are entirely mundane, even expected, explanations for any delay in data release. Spacecraft data undergoes rigorous processing pipelines. Raw images demand meticulous calibration, correction for inherent instrument artifacts, and thorough validation before they can be shared with the public, or even the wider scientific community. Mission teams operate under strict priorities. Mars orbiters exist primarily to unravel the mysteries of Mars itself, not to seize every opportunistic comet observation. Diverting resources and time from core mission objectives to image a fleeting comet requires significant justification, intricate scheduling, and often delicate negotiations between diverse science teams. It remains plausible that these observations were simply a low priority, undertaken only if convenient, rather than deemed essential. The data might still be languishing in processing queues, awaiting its turn behind more pressing tasks. Then there's the immutable reality of observing geometry. A comet's proximity to Mars doesn't automatically guarantee an easy shot for orbiters. Orbital mechanics dictate precise windows, communication schedules with Earth, coupled with spacecraft orientation constraints, all impose strict limits on what's truly feasible. Perhaps the Mars orbiters were simply not in the optimal position, or not configured to observe 3I Atlas effectively. Or, perhaps, attempts were made but technical glitches or even Martian dust storms interfered. While dust wouldn't obscure space-based cameras, it represents the unpredictable nature of operating in an alien environment. But what if the silence masks something more? What if these images do exist, have been processed, and are currently being held back, awaiting deeper analysis? What if their contents are so profoundly unusual that mission teams are compelled to meticulously triple-check every interpretation before releasing potentially world-altering data? Space agencies, by their very nature, are bastions of caution. They have, in the past, faced public embarrassment and a fracturing of trust when prematurely released data was later reinterpreted or corrected. If HiRISE or the ExoMars Trace Gas Orbiter captured anything truly unexpected within the inner coma of 3I Atlas, something that defies our standard models of cometary behavior, the immediate, instinctive response would be to verify and then re-verify with absolute thoroughness before any public announcement. History offers precedents for such prudence. When peculiar features are detected, when anomalies surface that could challenge established scientific paradigms or ignite sensational headlines, the data invariably undergoes an extraordinary level of scrutiny. Review boards are convened. Every conceivable alternative explanation is exhaustively explored. Only when teams achieve a profound confidence in their understanding, or, perhaps, a profound confidence in their lack of understanding, after all mundane explanations are exhausted, does the data finally see the light. This meticulous process can stretch for months, or even years. Beyond scientific caution, a delay could also stem from political or bureaucratic complexities. Space agencies exist as government or intergovernmental entities, always navigating a delicate balance of public relations, funding pressures, and international cooperation agreements. If findings from one mission were to significantly impact the interpretation of another, or touch upon sensitive geopolitical topics, coordination delays might become inevitable. as various stakeholders strive to align their messaging. It may sound cynical, but these vast organizations do not operate in a vacuum. They traverse intricate landscapes of public perception, scientific integrity, and deeply entrenched institutional interests. Some observers have, perhaps unfairly, ventured into deeper speculation. What if the Mars orbiter images reveal clear evidence of artificial structure or unambiguous anomalies that would fundamentally force us to rethink the very nature of 3I Atlas? Such images, they argue, might be deliberately withheld. The logic suggests that extraordinary claims demand extraordinary caution. Releasing such data prematurely could unleash a torrent of media hype, widespread public confusion, and immense pressure on scientists to provide answers they simply do not yet possess. It might be deemed wiser to wait, to withhold, until a more complete picture emerges, until multiple lines of evidence converge into a coherent, undeniable narrative. This line of thought, of course, quickly veers into the realm of conspiracy theory. We must tread carefully, for there is no concrete evidence of a coordinated cover-up. No leaked memo, no whistleblower has come forward to suggest anything astonishing is being deliberately concealed. What we are left with is a stark absence of expected data, and the deeply human tendency to fill such information voids with our own imaginings. The silence might mean nothing at all, or it might mean everything. We simply do not know. The true frustration of this absence lies in the profound clarity the Mars orbiter imagery could offer. If the images were to depict a perfectly normal coma, devoid of the sunward jet or any other peculiar features, it would cast significant doubt upon our ground-based observations. Conversely, if they were to clearly confirm that sunward jet from a unique vantage point and with high resolution, it would solidify its reality beyond any reasonable doubt. And if, within the inner coma, they were to reveal hints of internal structure, perhaps a striking symmetry or focused venting, such details would fundamentally reshape our current models. The data, we presume, exists in some form. We are merely left to wait for it to finally emerge from the intricate institutional machinery. A whisper from Mars that could change everything. Yet, this Martian silence is not the sole unsettling coincidence orbiting 3I Atlas. In the crucial days surrounding the comet's perihelion, when its behavior grew most erratic, a series of other strange occurrences rippled through our near-Earth and solar environment. Viewed collectively, they begin to form a pattern that could be mere chance, or it could whisper of something far more coordinated, a deeper causal connection unfolding across our cosmic neighborhood. Part 9. Echoes in the Cosmic Neighborhood. We are left to ponder, what if the peculiar behavior of 3I Atlas is not an isolated anomaly? What if instead, its erratic journey is merely one thread in a larger, more intricate tapestry of events unfolding around us? Between October 11th and October 14th, 2025, a startling cluster of phenomena captivated solar observatories. 4 distinct sun-grazing objects were reported, each hurtling relentlessly towards the sun. These celestial divers, meticulously tracked, seemed to emanate from roughly the same region of the sky as 3I Atlas itself. They plunged into the solar inferno, some dissolving into vapor, others simply vanishing into the blinding glare of our star. Sun-grazing comets are, in themselves, not uncommon. The renowned Kreutz family, believed to be fragments of a colossal progenitor comet that fractured centuries ago, regularly dispatches its members on suicidal dives toward the sun. Solar observatories beautifully catalogue dozens of these doomed wanderers each year as they succumb to the sun's unimaginable heat. Yet, the precise timing of this particular cluster is undeniably curious. 4 distinct objects, appearing within just 4 days, all originating from a remarkably similar direction in the sky. This surge directly overlapped with the period when 3I Atlas was displaying its most anomalous behavior and nearing its own perihelion. Is this merely a cosmic coincidence? Statistically, perhaps. The vastness of space near the Sun is a busy thoroughfare, constantly traversed by countless small bodies. Our ever-improving observational capabilities, especially from advanced space-based solar telescopes, mean we are detecting more of these fleeting objects than ever before. To find 4 in such quick succession during an active solar period is not statistically impossible, nor even particularly unlikely. Still, the sheer clustering of these events gnaws at the imagination. Could these sun-diving objects somehow be related to 3I Atlas? Could they represent fragments shed from the main body earlier in its journey, following subtly different orbits that ultimately converged on the Sun around the same time? Cometary nuclei are notoriously fragile. The relentless forces of solar tides, intense thermal stresses, and even rotational instability can cause them to shatter into multiple pieces. If 3I Atlas had indeed shed fragments months or even years ago, those smaller pieces might well have developed slightly divergent orbits from the main nucleus, leading them to reach perihelion at staggered times. We have witnessed this phenomenon before. Comet Shoemaker-Levy 9 famously fragmented before its dramatic collision with Jupiter, creating a spectacular string of pearls that impacted over several days. Spectroscopic analysis of these sun-diving objects would be the definitive test of this hypothesis. If their chemical composition were to match the unusual chemistry of 3I Atlas, it would profoundly strengthen the connection. If they presented a more typical cometary composition, the link would likely dissolve. However, obtaining detailed spectral data from objects on the brink of solar incineration is an immense challenge. They are often faint, incredibly fast-moving, and visible for only the briefest moments. Most sun-grazing detections rely on coronagraphs, instruments designed to block the sun's blinding disk and reveal its faint surroundings. These images, while crucial for detection, typically do not provide the spectral information needed for such a definitive comparison. During this same tumultuous period, another peculiar event captured widespread public attention, though its true nature remains even more elusive. In mid-October, during a SpaceX Starship launch, observers meticulously analyzing video footage of the spacecraft set against the luminous backdrop of the moon noted a distinct, bright point of light. It appeared near the lunar glare. This point seemed to hover for several seconds, in a position that defied alignment with any known satellite, star, or planet. Then, as quickly as it appeared, it vanished. The internet, as expected, immediately ignited with a flurry of speculation. Was this a genuine, unidentified object? A clandestine spacecraft, perhaps? Or a rogue piece of debris? Or was it merely an optical artifact? A lens flare? A deceptive reflection within the camera's intricate optics? Lens flares are, after all, a common occurrence in astrophotography, particularly when a brilliant object like the moon dominates the frame. Light can scatter within lenses, reflect off sensor surfaces, creating ephemeral, ghost images that manifest as bright spots or streaks. Discerning between a true celestial body and a camera artifact demands rigorous analysis of the original footage, a deep understanding of the camera system, and ideally, corroboration from multiple, independent cameras. In this specific instance, such definitive analysis has remained frustratingly inconclusive or entirely absent from public reporting. While the bright point could be something real, it is equally, if not more, probable that it represents a mundane optical illusion. What lends this seemingly disparate event a tangential relevance to 3I Atlas is, once again, the timing. The Starship launch occurred in mid-October, precisely overlapping with the period of heightened cometary activity and the unsettling cluster of sun-diving objects. For those predisposed to seeking patterns, a connection inevitably begins to form in the mind. Could this bright point near the Moon be intrinsically linked to whatever force is driving the anomalies of 3I Atlas? Could we be witnessing some coordinated activity, a hidden phenomenon subtly influencing multiple objects across near-Earth space simultaneously? It is here, however, that we must deliberately apply the brakes to our runaway speculation. Coincidences, after all, are an undeniable part of the cosmic tapestry. We, as humans, are profoundly wired as pattern recognition machines, honed by evolution to discern connections even where none truly exist. In our distant past, false positives were often less costly than missed warnings. Thus, our brains automatically construct narratives linking seemingly unrelated events. This inherent tendency does not, however, validate the reality of those connections. Yet, let us indulge the idea for a fleeting moment, not as a serious hypothesis, but as a provocative thought experiment. Imagine a singular cosmic event, a powerful pulse, or a profound disruption rippling through the interplanetary environment, simultaneously affecting multiple small bodies. Could a sudden burst of high-energy particles from the Sun, perhaps a coronal mass ejection with truly unusual properties, or even an anomalous density wave in the interplanetary medium, trigger such widespread effects? Could such an event induce sudden outgassing in comets, subtly destabilize their orbits, or interact with dust and debris in ways that generate transient optical phenomena? The underlying physics would be extraordinarily complex to model, but in principle, it is not entirely impossible. Coronal mass ejections, for instance, are colossal eruptions of plasma and magnetic fields from the Sun, surging through the solar system at immense speeds. When they collide with Earth, they ignite geomagnetic storms, dazzling auroras, and can disrupt satellites and power grids. When they encounter comets, they are known to compress the coma, intensify the ion tail, and even trigger dramatic outbursts. If a particularly potent or unusual CME occurred in early to mid-October, it could plausibly have influenced both 3I Atlas and other bodies scattered across interplanetary space. Solar observatories maintain a constant vigil for such events. A swift review of solar activity reports for October would quickly reveal any significant CMEs or solar flares during the relevant period. If such an event is identified, it could offer a compelling, natural explanation, linking some of these perplexing observations. If not, we are once again left to grapple with the most likely explanation: mere coincidence. The sun-diving objects, the enigmatic starship Brightpoint, and the anomalous behavior of 3I Atlas might simply be unrelated occurrences that, by pure chance, clustered together in time. Or they might be subtly connected by some profound, underlying cause we have yet to identify. Without more definitive data, we remain suspended between these possibilities. What we can state with certainty is that October 2025 has unfolded as an unusually eventful chapter in the annals of near-Earth and solar system astronomy. And at the very heart of this tumultuous activity stands 3I Atlas, the most anomalous, the most intensely scrutinized object in the entire cosmic mix. Yet, 3I Atlas is not the solitary interstellar visitor to shatter our established assumptions. It is part of a grander progression, a series of enigmatic objects arriving from beyond our solar system, each one seemingly rewriting the rules of celestial mechanics in its own unique way. To truly grasp where 3I Atlas fits within this unfolding cosmic drama, we must turn our gaze backward to its predecessors and ask a crucial question. Is there a discernible pattern emerging in the behavior of these interstellar wanderers? Art 10. The Cosmic Reversal. A pattern unveiled. 3I Atlas, this enigmatic visitor, may not be an isolated anomaly. Instead, its bizarre behavior could be a crucial piece in a larger, unsettling pattern, now emerging from the depths of interstellar space. It is a motif of profound reversal, where objects arriving from beyond our solar system fundamentally defy our expectations, challenging the very bedrock of our cosmic understanding. This strange journey began in October 2017, with Oumuamua, the first confirmed interstellar object detected traversing our solar system. From its initial sighting, Oumuamua was an enigma. It exhibited no visible coma, no trailing tail, not a single obvious sign of outgassing, even as it swept perilously close to the sun, a proximity that should have triggered a violent sublimation of any water ice. Initially, this stark absence of activity led astronomers to classify it as an asteroid. Yet, Oumuamua's trajectory whispered a different, complex story. As scientists meticulously tracked its path, they observed a subtle, persistent acceleration away from the sunday. This was no simple gravitational dance. Something unseen was propelling it forward. In the familiar realm of comets, such non-gravitational acceleration is common, a well-understood rocket effect born from outgassing. Material jets away from the sun-facing side, and the reactive recoil nudges the comet in the opposite direction. But Oumuamua remained stubbornly silent, visibly inert. No coma, no jets, no detectable gas. Still, it accelerated as if it were a comet in full cry. Explanations quickly proliferated, each more speculative than the last. Perhaps a faint hydrogen outgassing, invisible to our instruments, provided the thrust. Or maybe it was an unusually strong radiation pressure, acting upon an object of extreme thinness, shaped like a vast, delicate solar sail. Another theory posited solid hydrogen ice, an exotic and fragile substance, sublimating without a visible trace. Every hypothesis, however, stretched the boundaries of what we considered normal, demanding increasingly tenuous assumptions. And then there was its shape, a form unlike anything seen before. Observations suggested Oumuamua was extraordinarily elongated, perhaps 10 times longer than its width. A cosmic cigar, or even a flattened pancake. No asteroid or comet within our solar system possessed such an alien geometry. The scientific community found itself locked in intense debate, while most researchers leaned towards natural, albeit exotic, explanations. A vocal few, notably astronomer Avi Loeb from Harvard, suggested Oumuamua's properties were more consistent with an artificial origin, perhaps a light sail, or a probe dispatched by an advanced alien civilization. This idea, controversial to say the least, ignited public imagination, transforming Oumuamua from a scientific puzzle into a global touchstone for humanity's deepest question. Are we truly alone in the universe? Then, in August 2019, amateur astronomer Borisov discovered 2I Borisov, the second confirmed interstellar object. This visitor offered a comforting counterpoint. It behaved precisely like a normal comet, boasting a clear, vibrant coma, vigorous outgassing, and the familiar chemical signatures of water and carbon monoxide in expected proportions. Its normalcy felt like a collective sigh of relief. Researchers declared that interstellar visitors could be ordinary. 2I Borisov seemed to prove that not every object from beyond our solar system was destined to defy our rules. It was a comet. It acted like a comet. Its interstellar journey was extraordinary, yes, but its intrinsic nature was reassuringly familiar. But now, 3I Atlas has arrived, and the strangeness has returned with an unsettling vengeance. If Oumuamua was peculiar for what it didn't show, 3I Atlas is utterly baffling for what it does show, and in all the wrong places. A sunward jet where an anti-solar tail should be, nickel without a corresponding trace of iron, carbon dioxide emissions so dominant they drown out the expected water. Rhythmic pulses, almost like a mechanical heartbeat, echoing through the void. This object doesn't merely fail to behave like a comet. It seems to actively invert the comet's textbook, as if deliberately rewriting celestial mechanics. When these 3 interstellar visitors are placed in chronological sequence, a distinct, almost narrative pattern begins to emerge. First, Oumuamua, an object devoid of expected activity, yet propelled by a mysterious, unseen force. Second, 2I Borisov, a beacon of reassuring normalcy, conforming perfectly to our expectations. And now, 3I Atlas, an object exhibiting reversed activity and a chemistry so bizarre it feels deliberately disorienting. It is as if the cosmos itself is conducting an elaborate experiment, presenting us with a calculated progression of anomalies, observing how we grapple with the unknown. Or perhaps, more profoundly, it is teaching us that our rigid categories of comet, asteroid, and interstellar visitor are far too narrow, too provincial, born from a sample size limited to our single solar system. This brings us to a fundamental philosophical question. Are these objects mere outliers, statistical flukes that grab our attention precisely because they are so unusual, while countless ordinary interstellar travelers drift by unnoticed, too faint or too mundane to detect? Or are they the true harbingers, the vanguard representatives of a vast, unseen population of truly alien objects, forged under conditions so vastly different from our own solar system's birth that they are designed to violate our every expectation? The answer carries profound implications for our place in the universe. If the majority of interstellar visitors are, in fact, strange, then it is our solar system's comets and asteroids that might be the true outliers. Peculiar products of a specific set of formation conditions unique to our cosmic neighborhood, not representative of the galaxy as a whole. We would be compelled to radically expand our models, embracing a far wider spectrum of chemical and physical possibilities, and humbly accept that what we currently define as normal is merely local normal, not a universal truth. Conversely, if most interstellar visitors are indeed ordinary, and we are simply drawn to the noticeable oddities, then Oumuamua and 3I Atlas become fascinating curiosities, astronomical equivalents of rare birth defects or unusual circumstances that do not reflect the broader population. We would still strive to understand them, of course, but their existence wouldn't necessitate a complete rewrite of our cosmic textbooks. The reversal motif, this persistent tendency for interstellar objects to invert our expectations, might be revealing a deeper truth about the galaxy's breathtaking diversity. Star formation, after all, unfolds across an astonishing array of environments. Some stars ignite in the intense crucible of dense clusters, battered by radiation and powerful gravitational interactions. Others coalesce in serene isolation within the sparse, outer reaches of molecular clouds. The raw material itself varies wildly, its composition shaped by the metallicity of the region, the ancient history of enriching supernovae, and the proximity of colossal, luminous stars. Comets forged around a star in a metal-rich environment might possess a radically different chemistry than those born in a metal-poor one. Comets forming near massive stars could be subjected to far more intense radiation, irrevocably altering their surface properties, or preferentially driving off specific volatile compounds. 3I Atlas, with its perplexing carbon dioxide dominance and metal anomalies, could easily be a product of such an exotic birthplace. Perhaps it coalesced around a carbon star, a celestial body where carbon far outstrips oxygen in its outer atmosphere, leading to the creation of carbon-rich dust and unique chemical pathways. Perhaps it endured a long sojourn within a dense molecular cloud, where relentless cosmic rays processed its ices in unprecedented ways. Or maybe it is simply ancient, billions of years old, its surface irrevocably transformed by eons of exposure to the harsh interstellar radiation field. These are all natural explanations, elegant in their complexity, capable of accounting for its oddities without ever needing to invoke artificiality. Yet, the reversal motif also resonates with a more speculative, almost haunting interpretation. If interstellar space is occasionally traversed by probes or artifacts from other civilizations, these objects would, by their very nature, violate our expectations. They would not be products of random accretion or natural processes. Their materials would be chosen for engineering efficiency, not cosmic abundance. Their structures would be optimized for specific functions, not chaotic formation. They might possess systems that operate with rhythmic precision or directional purpose, precisely because they were built to do so. Within this framework, the reversal is no mere coincidence. It is a signature. Objects that break the rules might be breaking them because they were crafted by rule breakers. This brings us to a critical juncture in our understanding of the cosmos. 3I Atlas, Oumuamua, and the interstellar visitors yet to be discovered are relentlessly pushing us to expand the horizons of our thinking. Whether the ultimate explanation lies in exotic, yet natural cosmic processes, or something far more radical, we are being forced to confront the inherent limits of our current models. As we grapple with these profound cosmic puzzles, it is striking to note that 2025 has already proven to be a year of paradigm-challenging discoveries across an astonishing array of scientific fields. 3I Atlas is not occurring in isolation. It is emerging in a year where other fundamental assumptions are being rigorously tested. Dark stars are baffling cosmologists. Artificial intelligence is unearthing patterns in physics that humans have overlooked for generations. Quantum teleportation is achieving milestones once deemed impossible just decades ago. And fusion energy is finally crossing thresholds that promise to fundamentally reshape human civilization itself. Perhaps we are not merely witnessing isolated anomalies, but rather entering an entirely new epoch where such paradoxes are becoming the norm. A period where the universe is choosing to reveal complexities and wonders we had never dared to anticipate. Across every scale of existence we endeavor to study. Part 11. The Paradox of Primal Black Holes. Recent findings from the James Webb Space Telescope and other surveys have ignited an unexpected, profound debate in cosmology. They challenge our fundamental understanding of how the universe's first grand structures actually formed. The Standard Model, for decades, held a clear sequence. Galaxies emerged first, growing from tiny density fluctuations in the early cosmos. Then, within these nascent stellar islands, black holes gradually coalesced at their centers as matter accumulated and collapsed. This bottom-up process, building complexity from simple beginnings, felt entirely logical. Gas condensed into stars, stars clustered into galaxies, and eventually, enough mass concentrated to forge supermassive black holes. Yet JWST keeps revealing something deeply unsettling. Black holes that appear far too massive, far too early. We observe supermassive black holes, millions to billions of times the mass of our sun, already thriving when the universe itself was less than 1 billion years old. This timeline simply doesn't allow for their growth through conventional accretion and mergers. It presents a cosmic paradox. How could these gravitational behemoths achieve such immense scale in so little time? Did they begin their existence already colossal, exceeding our theoretical predictions? Or did they grow at an impossibly accelerated pace? Perhaps our entire understanding of the cosmic sequence is fundamentally flawed. This profound quandary has led to a radical idea. What if black holes formed first, before galaxies? What if they were the initial seeds, the gravitational anchors around which future galactic centers would eventually gather? This possibility gives rise to the concept of dark stars. Hypothetical, ancient objects powered not by the familiar nuclear fusion of ordinary stars, but by the intense annihilation of dark matter particles. Imagine dark matter, dense and clumped in the nascent universe, releasing immense energy as its particles self-destructed. This energy could heat surrounding gas, causing it to glow brightly. These dark stars could have been truly enormous, dwarfing any fusion-powered star we know. Their eventual collapse would create the very black holes needed to jumpstart galaxy formation. It's a complete inversion of the expected cosmic order. Black holes before galaxies, not the other way around. The evidence remains tantalizingly ambiguous. These observations, pushing the very limits of JWST's incredible capabilities, are still at the bleeding edge of discovery. Alternative explanations persist. Perhaps the black holes aren't quite as massive as they seem, or their accretion rates are far higher than our current models permit. Maybe our understanding of the universe's earliest conditions simply needs profound refinement. But the very fact that this conversation is happening, that the bedrock of our cosmological sequence is being questioned by hard observational data, speaks to a much larger truth. Our most cherished models are being rigorously tested, and in some cases, found wanting. The universe, it seems, is far more intricate, far more surprising than our neat theoretical frameworks ever anticipated. It makes one wonder, if we can be fundamentally mistaken about something as monumental as the formation of galaxies and black holes, the very structures defining the cosmos's grand architecture, then our potential misunderstanding of an interstellar visitor, like 3I Atlas, feels almost inevitable. Both scenarios highlight a recurring pattern. We extrapolate from limited samples, assuming universal application, only to discover the cosmos holds unexpected tricks. The debate over dark stars provides crucial context for our ongoing discussion of 3I Atlas. We are not in an era of settled science, where all the grand questions are resolved and only minor details remain. Instead, we find ourselves in a period where foundational assumptions are being vigorously challenged across multiple scientific domains. Of course, not every anomaly signals a revolution. Most turn out to be measurement quirks, calibration issues, or familiar phenomena in new guises. But some anomalies are undeniably real, and a select few of these real anomalies compel us to rebuild our theories from the ground up. 3I Atlas might represent one of those theory-breaking anomalies, or it might simply be a breathtaking lesson in exotic, yet entirely natural cosmic chemistry. The critical takeaway is this: we cannot simply dismiss it because it doesn't conform to our current models. Our models, demonstrably, are incomplete. The universe is under no obligation to conform to our expectations, and recent discoveries are teaching us that lesson repeatedly and profoundly. Part 12. AI. Unveiling the Unseen Universe. The universe speaks in torrents of data, light curves, spectra, images. Yet, so much remains unheard, unseen. Human perception, for all its brilliance, is finite. We are drowning in information, especially when confronting an enigma like 3I Atlas. What if another way to listen, another eye to see, now exists? By 2025, artificial intelligence has transcended mere assistance. It has become a discoverer, unearthing truths that eluded human minds for decades. Machine learning algorithms, meticulously trained on colossal datasets, now recognize patterns, correlations, and subtle anomalies. These insights would take human researchers years, perhaps a lifetime, to uncover. This profound shift reshapes every scientific domain, and astrophysics stands at its new frontier. Consider recent papers in high-energy physics and cosmology. AI systems are increasingly listed as co-authors. This stark acknowledgement confirms algorithms contribute substantively to discovery. They are not simply data processing tools. They are hypothesis generators, sophisticated pattern recognizers operating in high-dimensional spaces where human intuition falters, where our senses cannot grasp full complexity. An AI, trained on galaxy spectra, can pinpoint unusual emission lines across thousands of celestial objects simultaneously. Another, analyzing the flickering light curves of variable stars, can discern periodicities deeply buried within noise, signals invisible to even the most vigilant human eye. This transformative capability holds immense implications for objects as perplexing as 3I Atlas. The sheer volume of data we possess, its spectra, images, fluctuating light curves, contains far more embedded information than any single human mind could fully extract. There are whispers of correlations between chemical abundances and mysterious activity patterns. Subtle timing relationships hint at deeper rhythms. Perhaps intricate spatial structures within its coma could betray a hidden internal organization. Imagine an AI trained on vast cometary data, then unleashed upon 3I Atlas. It might illuminate connections, explaining its perplexing anomalies, or flag entirely new oddities we haven't even begun to suspect. Yet, this formidable power is not without its shadows. AI systems can hallucinate patterns within pure noise, weaving narratives where none truly exist. They can overfit to training data, inadvertently learning the quirks of specific instruments rather than the universal language of physical relationships. Crucially, they can unwittingly encode biases inherent in their training sets, reinforcing old assumptions instead of boldly challenging them. An AI accustomed to the familiar ballet of solar system comets might erroneously flag every unique characteristic of 3I Atlas as anomalous, not because it defies physics, but simply because it deviates from its learned norm. The true strength lies in a symbiotic partnership, combining AI's unparalleled pattern recognition with essential human skepticism and profound physical intuition. Let the AI tirelessly scan for the strange, the unexpected, the outlier, but then demand that human experts meticulously verify these findings, diligently check for artifacts, painstakingly construct robust physical models to explain them. This hybrid methodology already revolutionizes fields like gravitational wave astronomy. AI swiftly flags potential signals amidst detector noise, allowing human experts to critically evaluate whether these are genuine cosmic events or mere instrumental glitches. This very same approach could utterly transform how we study our enigmatic interstellar visitors. What if? Just imagine an AI system capable of ingesting every single observation of 3I Atlas, every fleeting spectrum, every pixelated image, every precise timing measurement, tirelessly searching for hidden correlations. It might unveil that the mysterious 4-hour pulse is intricately linked to specific spectral line strengths, hinting at a complex chemical cycle. It could discover that the intensity of its sunward jet fluctuates in direct relation to its nickel-to-iron ratio, suggesting a shared, underlying driving mechanism. It might even identify subtle precursor signals, minute changes in the coma hours before an outburst, offering us the unprecedented ability to predict future activity. Or, perhaps, it might find nothing at all. That outcome, too, would be profoundly valuable. It would confirm that we haven't overlooked obvious connections, that the mystery surrounding 3I Atlas is indeed genuinely mysterious, a profound puzzle without an easy answer, a quiet thought. Sometimes, confirming the absence of a pattern is a discovery in itself. The year 2025 marks a pivotal threshold in the very fabric of scientific inquiry. We are no longer merely using computational tools. We are augmenting human intelligence with machine intelligence in fundamentally different ways. This paradigm shift redefines the boundaries of what is possible, what questions we can even dare to ask, and with what astonishing speed we can hope to answer them. If 3I Atlas harbors secrets deep within its voluminous data, AI could very well be the singular key to unlocking them. And should AI robustly confirm that the anomalies are not isolated, but interconnected and persistent, it would dramatically strengthen the case for more exotic explanations, whether natural or, perhaps, something far more profound. Part 13. Teleportation's unsettling reality. Imagine information that simply vanishes from one point, only to instantly reappear at another, never traversing the intervening space. It sounds like magic, a myth made real. Yet, in 2025, this very concept is quietly becoming routine in quantum physics. A mere decade ago, such an achievement was unthinkable. Now, researchers have successfully teleported quantum information across 56 kilometers of standard fiber optic cable. Crucially, this wasn't in a sterile lab. This quantum data flowed alongside ordinary internet traffic within the same cables delivering your emails and video streams. This isn't theory. It is a verified fundamental shift. The breakthrough emerged from scientists at Northwestern University, collaborating with multiple institutions. Their work demonstrated quantum states could be reliably transferred with over 90% accuracy across metropolitan distances. The equipment integrates seamlessly with existing infrastructure. This is a profound revelation. Pause and truly grasp this. The fiber optic lines piping Netflix into your home, the networks beneath our cities carrying banking transactions and medical records, these now carry quantum information. Reality itself, in its most probabilistic form, flows alongside your daily news feed. This underlying mechanism challenges anyone who perceives space as merely an inert void. It hinges on quantum entanglement, a peculiar, unbreakable link between two particles. This connection is so instantaneous that Albert Einstein famously called it spooky action at a distance. When two particles become entangled, their fates are inextricably bound. Observe one, and its distant twin reacts instantly, without delay, regardless of separation by kilometers or light years. There is no transmission time, only a shared, immediate reality. The physicists orchestrating this phenomenon meticulously prepare pairs of entangled photons. One carries the quantum state they wish to transfer. Its partner waits at the destination. The critical step involves measuring the first photon and an intermediary particle. This act forces the distant photon to instantaneously collapse into the exact state of the original. The information, in essence, vanishes from its origin. It instantly materializes, whole and perfect, at the destination. No signal visibly traverses the space. No message passes through the void. The correlation is absolute, instantaneous. Einstein, in his era, found this deeply unsettling. He labeled it ghostly, unacceptable, a profound violation of physics as he understood it. Yet, in 2025, we are not just observing this ghostliness, but actively harnessing its unsettling power. But here, the true implications begin to crystallize. This process demands timing of such exquisite precision that error correction becomes a complex dance. Every entangled photon, a fragile whisper of reality, must traverse fiber optic cables, an environment hostile to delicate quantum states, thermal noise, subtle vibrations, electromagnetic interference. These are constant threats. They conspire to decohere the quantum information before it arrives intact. Yet, the researchers found a path through this fragility. Their solution involved sophisticated techniques, advanced filtering, superconducting detectors chilled to mere fractions above absolute zero, and active feed-forward protocols. In these, classical information about measurement results travels alongside the quantum signal. This classical data provides the receiver with a precise instruction set, a blueprint that perfectly reconstructs the quantum state. It's akin to sending a coded message, but simultaneously transmitting the exact quantum key needed to decode it. That key, however, is itself quantum and demands extraordinary protection. The distances involved, while not vast on a cosmic scale, are truly immense. By the delicate standards of quantum systems, 56 kilometers is an astonishing span over which to maintain quantum coherence. The fact that this feat is now repeatable, capable of consistent results time and again, signifies a profound transition. It marks the shift from laboratory curiosity to a viable, practical technology. This quiet revolution is already reshaping our understanding of communication. The implications for deep space communication are nothing short of staggering. Envision future probes venturing into the outer solar system, or beyond, into interstellar space. Traditional radio signals are plagued by inherent limitations. They degrade over immense distances, demand colossal power, and are forever bound by the finite speed of light. A transmission to Mars can take from 4 to 24 minutes. A message dispatched to the venerable Voyager probes requires a painstaking 18 hours. This isn't due to signal weakness. It's a fundamental constraint of light itself. A quantum communication link, however, would fundamentally alter this paradigm. It would establish a secure channel where any attempt at eavesdropping instantly destroys the quantum signal, immediately alerting both sender and receiver to intrusion. This security is absolute, not merely through encryption, but by the very unyielding laws of physics themselves. Even more profoundly, quantum communication could unlock distributed quantum computing. Imagine distant quantum processors collaborating on the same complex problem in true real time, unburdened by the light speed lag that cripples classical communication. While we cannot transmit information faster than light, quantum entanglement offers a pathway to coordinate processes in appearing almost instantaneous. The cosmos, it seems, has bestowed upon us an extraordinary gift: the ability for particles, separated by unimaginable distances, to behave as if they are a single, unified system. Here, a new analogy begins to form. Picture fiber optics not just as inert conduits, but as living, pulsing blood vessels carrying the essence of information through space. Classical fiber optics transmit discrete pulses of light, encoded as ones and zeros, the binary language of our digital age. Quantum fiber optics, by contrast, would carry something far more fundamental: raw quantum possibility itself. It's the difference between merely reading a detailed description of a landscape and actually standing within its vastness. It's the chasm between studying sheet music and truly experiencing the symphony. The information isn't a message about reality. It is reality, transferred intact from one location to another. Now, let us turn our gaze to the enigmatic comet 3I Atlas. What if, in a distant future, humanity dispatches quantum-equipped probes to intercept objects just like it? Such probes would demand instantaneous coordination, secure channels impervious to interception, and distributed processing power to analyze anomalies in real time. The very mechanisms poised to enable that future technology are being rigorously tested today. We are, perhaps unknowingly, laying the groundwork for cosmic communication networks of unimaginable scope. This progression leads us to a darker, more unsettling speculation, one that intimately links the mechanics of quantum teleportation to the enduring mysteries surrounding 3I Atlas. If quantum communication becomes commonplace, enabling advanced propulsion or truly exotic physics applications, could 3I Atlas itself be utilizing something akin to it? Not necessarily quantum teleportation as we currently comprehend it, but a sophisticated mechanism that exploits quantum phenomena to manipulate matter or energy in ways we cannot yet fathom. Consider 3I Atlas's perplexing characteristics: its rhythmic, unexplained outbursts, a chemical composition that stubbornly defies our established models, and coherent jets that seemingly should not exist on a body so small and icy. All these anomalies hint at a deeper manipulation of physics, operating at scales where quantum effects become profoundly significant. Stars, for the most part, behave classically. Planets, too, adhere to classical physics. But smaller celestial bodies, particularly those with complex internal structures of ice and organics, might operate within a regime where quantum phenomena genuinely hold sway. Quantum tunneling could allow particles to breach barriers they should classically never cross. Quantum fluctuations could ignite processes we are yet to comprehend. Entanglement between internal subsystems might forge correlations that appear utterly impossible by classical standards. What if 3I Atlas is not merely a comet? What if its inexplicable behavior reflects an environment or an engineered process that operates partially within the quantum realm, a place where superposition and entanglement are not abstract concepts, but tangible, mechanical realities? The very act of observing such an object, measuring it with our telescopes and spectrographs, would inevitably disturb its delicate quantum states. This interaction could potentially explain the bewildering inconsistencies between different observations, the shifts in brightness and composition that appear to change based on how we look at it. This is not a descent into madness. This is a logical extension of known physics into uncharted territory. The observer effect, that foundational pillar of quantum mechanics, unequivocally tells us that measurement itself alters reality. When we observe 3I Atlas, we are not passive spectators. We are active participants. We are collapsing superpositions, fixing properties that might otherwise remain in a fluid state of quantum uncertainty. The year 2025 marked a pivotal moment. We learned we could teleport quantum information through our existing infrastructure. The profound question that now lingers is whether the cosmos has been orchestrating something similar all along. Could objects like 3I Atlas be cosmic quantum computers, subtly manipulating their own states through entanglement and superposition, appearing strange to us only because we are observing the collapse of their infinite possibilities into our limited classical reality? Part 14. The unlocking of stellar fire. To hold a piece of the sun, to command its power, this was an ancient dream. For 4.6 billion years, our star has burned, fusing hydrogen into helium, unleashing more energy in a single second than humanity has ever consumed. Every warming photon, every life-giving ray, every pulse of our planet's weather, all born from that stellar furnace. For a century, scientists grasped the theory of fusion, but practical control, replicating its self-sustaining power on Earth, remained an impossible horizon. Until now, a quiet revolution has begun. On February 23, 2025, the National Ignition Facility in California achieved ignition for the 7th time in repeated experiments, setting a new record. Lasers, carrying 2.05 megajoules of energy, struck a tiny target. The fusion reaction erupted, producing 5 megajoules, nearly 2.4 times the input energy directly applied. This alone signaled a profound shift. Months later, on June 22, 2025, a collaborative team led by Los Alamos National Laboratory and Lawrence Livermore ignited fusion again. They generated 2.4 megajoules in a self-sustaining reaction, a burning plasma reaching critical conditions. Subsequent experiments have pushed this further, achieving 8.6 megajoules. The pattern is undeniable. Ignition is no longer an accident. It is repeatable. It is scalable. It is becoming the new baseline for what is possible. But how does one capture a star? Fusion, at its core, is elegantly simple, yet profoundly difficult. Two hydrogen atoms are forced together with such immense pressure that their nuclei merge, overcoming electromagnetic repulsion. The strong nuclear force takes hold. A new, slightly lighter helium nucleus forms. That tiny fraction of missing mass, as Einstein's equation revealed, transforms into an unimaginable burst of energy. The challenge lies in sustaining the millions of degrees required. Two primary paths have emerged. Inertial confinement, chosen by the National Ignition Facility, uses lasers so powerful they compress a minuscule fuel pellet in a fraction of a nanosecond. This creates the extreme densities and temperatures of stellar cores, if only for fleeting microseconds. Imagine the sun's core, squeezed to the size of a grain of sand that is the controlled implosion within the target chamber. The National Ignition Facility directs 192 separate laser beams simultaneously at a cylindrical casing known as a hohlraum. Inside, a capsule holds deuterium and tritium. The concentrated energy compresses this fuel to 50 times its normal density. Fusion ignites. Energy pours forth. The true breakthrough is not just that ignition happens, but its consistent, repeatable nature and accelerating efficiency. In 2024, the facility achieved a 120% energy gain on certain shots. The trajectory is undeniably upward. Meanwhile, other visionaries explore magnetic confinement. In April 2025, TAE Technologies announced a significant advance with their NORM experiment. They achieved their highest steady-state plasma performance using only neutral beam injection, eliminating complex quartz tube formation systems. This dramatically simplifies the apparatus. Simpler means cheaper. Cheaper means scalable. Scalable means commercial. The financial world is taking notice. Commonwealth Fusion Systems, backed by over $2 billion in private capital, has completed assembly of magnetic confinement systems for their spark reactor. They anticipate demonstrating net energy generation in early 2027. Private capital flowing into fusion speaks volumes. Business doesn't fund mirages. It funds the future. This is the true point of no return. We are transitioning from proving fusion's theoretical possibility to actively demonstrating its commercial viability. We are entering a new era where our fundamental understanding of energy is being rewritten. Classical physics often dictates that increasing energy density comes with escalating difficulty, cost, and environmental burden. Fossil fuels demand extraction, processing, transportation, combustion, leaving behind waste and greenhouse gases that alter our climate. Fission requires immense safety infrastructure, cooling systems, radioactive waste storage, and stringent security protocols. Fusion, however, exists in a category entirely its own. Two atoms merge, inert helium forms. The fuel, hydrogen isotopes, is abundant, dissolved within our oceans. The waste is minimal. The energy release is absolute. Fusion produces no carbon dioxide. It leaves no long-lived radioactive waste. It produces inert helium. It is, perhaps, the closest thing to magic that physics will ever allow. A startling parallel emerges. Just as fusion shatters our beliefs about energy production, forcing us to rethink economics and physics, 3I Atlas challenges our foundational understanding of small celestial bodies. We thought we understood comets, with models refined over decades, explaining what ice and rock could do under cosmic pressures. Yet, 3I Atlas is proving comets can be far stranger than predicted. Its anomalous velocity, its peculiar composition, the powerful, unexplained outbursts and jets, all suggest either profound incompleteness in our models or something truly unprecedented. Here lies the unsettling thought: what if the universe itself is signaling a shift? What if these anomalies, across multiple scales, are not isolated exceptions, but rather a nascent language we are only just beginning to decipher? Reflect on the recent timeline. In 2022, fusion ignition became a reality. In 2023, multi-node quantum teleportation networks were demonstrated. By 2024, quantum teleportation was achieved over existing internet infrastructure, proving the technology could scale, and in 2025, we witness fusion ignition, repeated, refined, accelerating toward commercial viability. Simultaneously, in that same year, 3I Atlas displays behavior that defies all established models. These events are not causally linked, yet they are profoundly connected thematically. They whisper of a universe operating with a flexibility and hidden depth far greater than our current frameworks allow. Energy can be unleashed through fusion in ways once deemed unscalable. Information can traverse quantum channels alongside classical data. Matter itself can behave in ways that hint at unseen complexities or unknown mechanisms. All of this converging within a single year. The implications compound with breathtaking speed. Fusion will soon offer humanity clean, virtually limitless energy. With such power, we can construct quantum networks on a planetary scale. These networks will coordinate distributed sensing, computing, and control of technologies we cannot yet even conceive. And if objects like 3I Atlas are revealing nature's hidden layers of complexity, then every new quantum network we weave, every fusion plant we activate, every sensor array we deploy becomes a tool for discovering what we have so profoundly missed. We are not merely building new technology. We are stepping into a new regime of physics. The universe, it seems, is preparing to unveil secrets it has guarded for billions of years. Part 15. A new reality unveiled. From the depths of interstellar space, 3I Atlas arrived, a silent enigma. Its trajectory alone presented a profound challenge, hinting at gravitational influences we simply cannot account for. The subtle perturbations implied forces acting upon this object, forces that, by all conventional understanding, should not exist in its cosmic vicinity. Then, there is its jet. Unlike any comet we have ever observed, 3I Atlas produces a continuous, coherent expulsion, cometary outgassing, as our models predict, should be a chaotic ballet of localized heating, unpredictable in both direction and intensity. Yet, the jet from 3I Atlas appears almost engineered, astonishingly precise, relentlessly constant. Its very composition further deepens the mystery, revealing materials that should not coexist under any standard cometary formation scenario. The chemistry simply does not align with objects forged in protoplanetary disks billions of years ago. Even its brightness, flickering with rhythms too regular to be accidental, too precise to be random, adds another layer to this cosmic puzzle. Moreover, its path has subtly drifted, suggesting a form of propulsion or momentum transfer far beyond mere outgassing, beyond any physical process we currently comprehend. These are not vague anomalies. These are not data points open to interpretation. These are direct observations that fundamentally falsify established models. They are not minor inconsistencies to be dismissed or errors to be corrected. They are undeniable signals that something profoundly different is at play. We stand at a precipice, forced to reconsider everything. This lone wanderer asks a question the universe has whispered for centuries. Are we truly ready for what lies beyond our current understanding? And 3I Atlas is not an isolated event. Consider the cascade of other breakthroughs in 2025. The theoretical concept of dark stars, where dark matter congregates around primordial black holes, has gained startling traction. These exotic entities could utterly redefine our understanding of stellar populations in the early universe. If dark stars are real, then the cosmos harbors untold numbers of objects we have never even conceived of, potentially outnumbering conventional stars by millions. Simultaneously, quantum teleportation has transcended theory, becoming a practical technology, demonstrated across metropolitan distances with astonishing fidelity. It reveals quantum mechanics to be far more exploitable than our textbooks ever dared to suggest. Fusion, too, has shifted from a distant dream to a repeatable reality, consistently achieving net positive energy gain. This monumental leap proves that energy production can be elegantly decoupled from combustion and fission, ushering in an era of stellar-scale power generation right here on Earth. Even artificial intelligence is joining the chorus of revelation. Advanced algorithms are now sifting through vast datasets, unearthing patterns that human researchers routinely missed. They are discovering profound relationships in physics that conventional analysis simply overlooked. Machine learning, trained on astronomical data, is unveiling correlations invisible to the human eye, identifying anomalies that we were perhaps too readily taught to filter out as mere noise. Every one of these threads weaves into a singular, undeniable thesis. 2025 is not merely a year of incremental scientific progress. It marks the undeniable dawn of a paradigm shift. For over 3 centuries, the bedrock of scientific inquiry has rested on a comforting assumption. Anomalies are typically errors, models are largely correct, and new observations serve to refine existing frameworks, not dismantle them. This approach has served us remarkably well, guiding us to profound understandings of gravity, electromagnetism, quantum mechanics, and relativity. But what if this fundamental premise is flawed? What if those persistent anomalies are not just noise, but powerful signals? What if our cherished models are not simply approximately correct, but fundamentally incomplete? What if the universe, in its boundless complexity, is far stranger than our current categories permit us to imagine, and we are only now beginning to glimpse its true strangeness? What if, all this time, we have been unconsciously filtering out crucial signals, conditioned to dismiss them as irrelevant static? Consider, for a moment, our very definition of natural. A comet, a wanderer of ice and rock ejected from a distant star system, drifting silently between worlds. That is natural fusion, the cosmic forge that powers our sun and sculpts elements in stellar cores, a process fundamental to the universe itself. That is natural. Quantum entanglement, a proven feature of quantum mechanics, tested and confirmed countless times. Undeniably natural. But what if 3I Atlas is also natural? What if our understanding of natural simply needs to expand, to encompass phenomena we do not yet grasp? What if being natural no longer demands conformity to our current models? What if it simply means existing without deliberate human intervention? By this expanded definition, 3I Atlas is unequivocally natural. It journeyed from the stars. It is not artificial. It was not engineered by human hands. Yet, its very existence, its every observed behavior, contradicts everything we believed we knew about objects in the vastness of space. A quiet unease settles, a recognition that our cosmic vocabulary might be tragically limited. The deeper, unsettling question emerges: are we systematically undercounting phenomena that simply refuse to fit our neat, predefined categories? Astronomy, for centuries, has diligently catalogued objects, stars, planets, asteroids, comets, black holes, neutron stars, brown dwarfs, each a carefully constructed box, complete with expected properties and behaviors. We meticulously place objects into these categories, and then we study the categories themselves. But what if some objects defy singular classification, spanning multiple categories simultaneously? What if there are processes at play that operate across scales we have not yet scrutinized with sufficient care? What if 3I Atlas is merely the vanguard, the first of many discoveries that will shatter our existing boxes? What if the universe has been patiently displaying these objects to us all along, and we simply lacked the conceptual tools, the very language, to recognize them? Consider the profound cascade of implications these revelations unleash. If dark stars truly exist, the universe holds entire populations of entities we have never studied, possessing properties and behaviors utterly unknown to us. We would be compelled to fundamentally rebuild our models of galactic structure, of stellar evolution, and of the early cosmos itself. If quantum teleportation can reliably operate through our existing infrastructure, then secure quantum networks can be deployed globally, unlocking technologies we cannot even begin to predict. Communication systems will be utterly transformed, computing paradigms will shift, and the very fabric of scientific inquiry will be reshaped. If fusion achieves commercial viability, the age-old specter of energy scarcity vanishes. Every technology currently constrained by energy limitations suddenly becomes viable. Climate change, once an insurmountable challenge, becomes solvable. The global economy will be irrevocably transformed. Material science will evolve beyond recognition. Space exploration, once a prohibitively expensive dream, will become affordable, practical, and routine. And if anomalies like 3I Atlas are not isolated exceptions, but rather harbingers, representatives of a vast, undiscovered class of phenomena, then our scientific models are not merely incomplete by degrees, they are missing entire foundational categories of physics. We are not simply refining our understanding. We are discovering that the universe possesses dimensions we never even suspected existed. What profound truths might the Hera array unveil as it meticulously tracks 3I Atlas? What astonishing images or data might the Europa Clipper spacecraft transmit if it encounters this object, or others like it, deep within our solar system? These are not merely academic inquiries. They are existential questions, probing the very essence of what natural signifies in a universe we are only just beginning to truly understand. The data gathered in the coming weeks holds the power to utterly reshape our fundamental conceptions of comets, of propulsion, of the astonishing capabilities of small bodies traversing space. It could reveal that 3I Atlas is not just an anomaly, but a precursor, a harbinger of an entirely new class of cosmic objects. It could demonstrate with chilling clarity that anomalies are not exceptions, but rather urgent signals that we have been modeling the cosmos with a dangerous, profound incompleteness. The universe, it seems, may be trying to tell us that our maps are missing entire continents, our physics textbooks are woefully incomplete, and our categories are far too narrow to contain the vastness of reality. A sense of fracture, a quiet breaking of old certainties. Here is the crucial, inescapable understanding. Every truly great discovery throughout human history has followed this precise, unsettling pattern. It begins with an observation that stubbornly refuses to fit the prevailing model. Initially, it is dismissed as an error, a perplexing anomaly, but through persistent observation and rigorous measurement, an undeniable truth slowly emerges. The model itself was fundamentally flawed. Newton's understanding of gravity, though revolutionary, was ultimately incomplete. Einstein provided the elegant correction. Maxwell brilliantly charted electromagnetism. Yet quantum mechanics later revealed light and matter to be far more intricately entangled than classical physics ever allowed. Each successive generation invariably discovers that the models of the one before it were incomplete, imperfect. Ptolemy placed Earth at the universe's heart. Copernicus courageously shifted the perspective. Kepler meticulously refined the planetary orbits. Newton articulated the universal force. Einstein wove space and time into the cosmic tapestry. Dirac boldly predicted antimatter. 2025, it now seems, may well be the year when we confront the stark realization that our current models of comets, of energy, of information, of the very nature of the cosmos, are not merely incomplete, but are missing entire, profound dimensions of physics. The universe itself is not broken. Our understanding, however, undeniably is. So, stay vigilant. Watch the incoming data with unwavering attention. Scrutinize every detail Hera observes. Monitor every report from our interplanetary probes. Listen intently to the patterns artificial intelligence uncovers in the vast datasets we can no longer manually analyze. The universe is poised to tell us something utterly unexpected. It always has. 3I Atlas is not merely an object. It is the first clear voice in a conversation that is about to become overwhelmingly loud. In the coming months, we will discover whether our long-held models can withstand this new reality, or whether reality itself is stranger, deeper, and infinitely more wondrous than we ever dared to imagine. The next transformative chapter of physics is being written now, in real time, across the cosmos. Pay attention, for everything is about to change.